Have you ever wondered how fast a small firework rocket leaves the launch tube, or how much force a tiny rocket motor actually produces? In this video, we'll answer those questions using nothing more than a slow motion video, a few simple measurements, and some basic physics. By the end, we'll estimate the rocket's launch speed, acceleration, and even its thrust. This is a rocket used in the experiment. It's a typical consumer firework rocket, about 5 inches long with 4 fins for stability. Before launch, I measured its mass to be 39.18 grams. Knowing the rocket's mass is important because Newton's second law relates force, mass, and acceleration. Once we determine the acceleration from the video, we can estimate the thrust produced by the rocket motor. The launch is recorded with my iPhone at 165 frames per second. During the playback, the video runs at a normal speed of 30 frames per second. That means that every second of real time appears stretched to 5 1/2 seconds on the screen. This slow motion effect allows us to measure the rocket's motion much more accurately than we could with the normal video. This is the video of me actually recording the shooting up of the rocket, and we're lighting it. This is normal time, normal speed right now. And there goes the slow motion where I started the slow motion on the recording. So you can see it's flaming out of the bottom of the rocket, and then you hear the whistling sound as the thrust builds and builds, and finally it's getting ready to take off. When it takes off quick. There it goes. There's only a couple, 3 frames to figure out exactly the total time it took for launch. So it had to be pretty quick, and that's why the slow motion was important. Using Clipchamp, a video editor, I added a time scale to the slow motion video. The rocket leaves a launcher at approximately 34.56 seconds and reaches the yardstick about at 35.66 seconds. The measured travel time on the slow motion video is therefore 1.1 seconds. Since the video has been slowed by a factor of 5.5, the rocket actually covered the first yard in only 0.2 of a second. I repeated this experiment with another rocket and obtained very similar results, giving confidence in the measurement. Now let's calculate the rocket's average speed. Average speed is simply the distance traveled divided by the elapsed time. The rocket traveled 3 feet, or 1 yard, in 0.2 of a second. This gives an average speed of 15 feet per second, which is approximately 10.2 miles per hour. All that may seem slower than expected. Remember, this is only the first yard of flight. The rocket is accelerating rapidly during this part of the launch. Since the rocket begins from rest, we can use one of the basic equations of constant acceleration. Solving the equation for acceleration and substituting our measured distance and time gives an acceleration of 45.17 meters per second squared. Divided by the acceleration due to gravity shows that the rocket is accelerating upward at about 4.7 Gs during the first yard of flight. Now we can estimate the thrust produced by the rocket motor. Newton's second law tells us that the net force acting on an object equals its mass times acceleration. Multiplying the rocket's mass by its measured acceleration gives the net upward force required to accelerate the rocket. However, the rocket motor must also support the rocket's own weight. Adding these together gives an estimated thrust of 2.2 newtons during the first part of the launch. This experiment shows how much information can be extracted from a simple slow motion video. By measuring only distance, time, and mass, we estimated the rocket's launch speed, acceleration, and thrust using basic physics. I would like to thank my brother-in-law Dan for helping me with filming of this experiment. If you enjoyed this video, please consider subscribing for more physics demonstrations and real-world engineering experiments. Thank you for watching, and I'll see you in the next video.